Thank you so much. Thank you so much, Elena and DBI. Obviously, DBI is really famous in the field of fire safety, so I was looking forward to this visit, and I'm very happy to be here today. So as Elena said, I'm Guillermo. I am a professor of fire science in the Department of Mechanical Engineering at Imperial College. This is in London. When you go to London to the museums, right, between Hyde Park and the Science Museum and the Natural History Museum, that's literally where we are. We have a fire group there. It's called Hayes Lab, and this is the fire group. So this is them. These are the students, not the current ones. These are historical students and postdocs that have been passing through the group. And Francesco is here, right? That's over there. That's Francesco when he was a student and also a postdoc. So if I were to, I'm going to be talking about batteries, but I want to emphasize our specific point of view, which could be summarized as diversity. We have a very wide range of diversities. We have many different engineering disciplines. We have chemical engineers, civil engineers. Obviously, we have mechanical engineers, mechanical engineer. We also have physicists. We have a wide range of skills, which is very important to look at the same problem from different angles. And then when we do the work, when we study science, we love to combine the modeling with the experiments. It is difficult to ideally you want a group that are experts in modeling, or that are experts in experiments, because you can defend your turf, so to speak. In reality, the 21st century is the combination of the two. So when we can combine the two, if it's possible, we love it. We absolutely love it, but not always. In the work that I'm going to show you of batteries, it's not only the work that we've done, it's an overview, but when it's the work that we did, I'm proud to say Francisco was essentially in this, that we were able to combine modeling and experiments, although I'm not talking about that much today. So I just want to talk about batteries. And when we talk about batteries, I would like to express to you an issue that we have in the field. You have it here as well. We have it all around the world, which is that we have the ability to tell two stories about what is happening with fire safety. And we, each of us, decide which narrative we follow. And as an academic, I realized about this duality that I had myself, that depending who I was talking to, I could tell the story from one narrative or the other. So I realized I have dual personality in this field. So one possible narrative is when you look at the production of plastics, of polymers. I'm a mechanical engineer, I love polymers. But all polymers, synthetic polymers are, and the natural ones, are flammable. All of them are combustible. It's just a level, there are degrees, right? They could be extremely flammable. They're not allowed to be close to a human, at least legally, or they are very little flammable and it's okay. But they're all flammable. So when you look into the production of polymers, since they were invented right before and after the Second World War, you can see that it's an exponential growth. We humans, this planet, is addicted to polymers. And right now, polymers don't have a very good image. But anyway, we still use them tremendously because all of them are flammable. And all these polymers are close to humans. We are facing, some people, this is narrative, we are facing catastrophe. We are surrounding ourselves with more flammable materials in an increasing amount, in increasing types. The walls, the floors, the ceilings, the gadgets, our clothing, is this incredible arrival of polymers. So this is the doom scenario, which can be summarized as we're all going to die, right? And then this is the narrative that I use and some other people use when you want a response from the audience and you want them to embrace fire safety because they have to embrace fire safety to stop this scenario, right? The other narrative, and we literally, as we could do this, is you can look into statistical data. The best statistical data sets are typically in North America. The UK has also really good data sets, in particular the city of London where I live. But also, although you can do this in many countries, when you look into not the trend of 1 or 2 or 3 years, when you look at a big trend, especially more than 20 years, you see that we are doing really well at decreasing the number of fires, at decreasing the number of fatalities, at decreasing the number of injuries from fire. This is, and the signal is very, very clear. No matter that you actually go up and down, this is specifically for London. These are the number of fires per million dwellings. So it's even the city continues growing, and the number of fires keep actually decreasing even more per person, right? So it's very straight. You can do this with many, many data sets. I could actually choose to just show you this one over here, right? Where it was a year where the safety was not very good. But when you take a wide range, they always go down. So this is the other narrative. This is the narrative of, we are doing great, don't touch anything because it's working, right? And this is the narrative that we choose when we want the audience to stop changing the standards, to start bringing strange things because we want them not to move. So we guys, literally each of us, decide which narrative we run. But it's very difficult to be neutral. Because I realized about this, I wanted to discuss how come these two narratives are possible. How come we can say we're all going to die at the same time as we say we are doing great, just keep doing it, right? And the reason is three. There are three reasons for this. The first one is us. It is literally us that are making sure that this is looking this pretty. We have more fuel, we have them everywhere, yet there are less fires and less victims. That's because fire engineering. So we could celebrate that. So we are part of the conundrum that happens with the two narratives. The other one is fire injustice. It's a topic that is growing a lot, is that all these fires are not happening, all these fires that you can see over here, sorry, because of these flammable materials, are not happening to everybody. They happen with more frequency to people who are more vulnerable, who have less defense. So the success maybe is in the people who can afford more protection, whereas the people who cannot afford more protection are actually suffering the same amount or an increasing amount of fire. So it's unfair distribution of the fire burden. And the third one, which is, you're wondering, is when are you going to talk about battery fires, is the concept that I call innovation blind spots, which is innovation has brought something new. I'm an engineer, I love innovation, I love new things. They were dreamed by scientists and engineers to address one need or wish of society. It is already here and is bringing unintended consequences, which for us means that are bringing a new fire hazard. And because it's innovative, it's new, and because it's not in great numbers, we cannot see them in the statistics. When we look into statistics, which is where we see the big picture, we don't see these problems. We are blind to them. It is happening. It is not that they're not happening, it's that we don't see them. And these are innovation blind spots, and we have many of them. The idea with the innovation blind spot is they start as innovation blind spots. There is a new hazard, a new fire hazard. Some people might be talking about this. I've been hearing people talking about battery fires for a long time, long time ago. But there were more people saying, it's absolutely fine, this will never happen, don't worry, it was a fluke, and it's very difficult to make these things catch on fire. And then the blind spot continues growing, and it starts morphing, and society is not responding to this, authorities are not aware of the issue, and suddenly it becomes the elephant in the room. So I do believe that batteries is an innovation blind spot. Once upon a time, innovation blind spot. Now there are very significant amount of science that says this is the elephant in the room. It is really difficult not to realize that we do have a problem. I love innovation. I love batteries myself. I'm the user of several batteries today. And when I get back home, I'm going to have even more over there. But I am concerned about the hazard that we have brought into our homes and offices and industries. So another one you might be familiar with, an innovation blind spot that became an elephant in the room is facades. I'm from London. We discovered this in Grenfell in 2017. This was already happening. The authorities in the UK were saying, what are you talking about? This is all fine. People were saying, I saw that in China there was a fire. I don't know what you're talking about. I saw that in South America. I don't know what you're talking about. And then when it was in the news, it was in front of them, and they were actually going to court, then it was like, oh, actually, you were right. And now we have to do something about this. How many buildings do we have in the UK that have this facade? Probably is what, 1,000 of them? And when they counted, they were in the thousands of them, right? So it was an innovation blind spot that then became the elephant in the room. Now the UK, I think you're familiar with this, is in big trouble what to do with these buildings that are known to have a problem. And they will be addressed, and we'll be very happy about this, but it's costing money, and it requires a type of leadership that the country maybe right now doesn't have. This is one of the proofs why the elephant of batteries is in the room. I gave this presentation in 2022 in summer. I happened to be in a conference in Vancouver, and precisely as I was preparing to go to Vancouver, I seen the news that the city of Vancouver in Canada, it's a beautiful city by the way, had become the first city in the world where the leading cause of fire death was battery fires. They were in the news because this was unusual. It was a blind spot that suddenly was becoming something in front of them. So the London Fire Brigade, the Vancouver Fire Brigade, were asking, what is this? So I said, well, you know, I've done some of the research on this. I am in the city. And they said, please give a talk. And I gave a talk precisely because they had the leading cause of fire death was in lithium-ion batteries. Now the leading cause of fires is becoming, in London, is becoming lithium. Not the number of fire deaths, fingers crossed, but one of the incoming leading causes of fires in the city of London is battery fires. How does the London Fire Brigade know about this? Because for the last 5 years, they started to have reports where there was a little box that says lithium-ion batteries. Before, battery fires were happening, but the London Fire Brigade didn't have a little box to say lithium-ion batteries. We were blind to this innovation. So why do we care about batteries? You probably know this, but it's important not to remember, not to forget. We all have batteries. A battery is a reactive material. This is uncontroversial. Actually, that's why they are so good at storing energy, because they are able to react and deliver this energy in the form of electricity on demand. They are amazing devices. This energy that they have stored can also be released in unintended consequences, not electrically, but thermally. It's unintended. They are actually on-purpose systems, so it doesn't happen, but sometimes it happens, and because they are so powerful and so small, when it happens, they become an ignition source. And this is one of the worries, not the only one, that we have with batteries. Batteries are flammable, but pretty much everything that we have around ourselves is flammable unless it's steel and concrete. So the batteries are not concerning because they're flammable. We can handle this. We're fire engineers. It's because they are flammable and they are an ignition source together, prone to failure with some small number, and they are very close to people. So as a fire engineers, you are like, oh, fantastic. Who invented this? Right? It's almost like it's the dream of an arsonist. It's not the dream of an arsonist, unfortunately enough, because the number of failures is 1 every several million, right? So just because we have that number, 1 in many million, people are saying, don't worry, because it could happen, but it just doesn't happen. Oh, great, it makes me feel really comfortable when we have a battery at home. So they pose a hazard for different reasons. I'm going to show you this video. You might have seen it. It's one of the most famous videos of battery fires. It's an electric car. I know you really like electric cars here in DBI, and you're studying the safety of electric cars, but I worry more about the safety of all batteries, from really small ones to very large ones. Right? Just an example, because it became very popular. But I use this image because I think it's running. Yeah, it is running. Because as a fire engineer, you can learn many things. So this car of a very known brand is in trouble. This car is already, from my point of view, is on fire. And people say, it's not in fire, Guillermo, I don't see the flames. I say, you don't have to, I happen to be an expert in the smoldering combustion, which is flameless combustion. You don't have to have a flame to actually be on fire. That, according to Semenov, who got a Nobel Prize in '56, there had already been a thermal runaway, which is an ignition event, and then they came outside and you saw the flames. So people say, that was when the fire is, and I say, no, the fire probably started about half an hour ago, when the battery started to be exothermic in an uncontrolled way and in a very increasing fashion. So there was no previous sign. This car the battery had ignited, you could not tell. All the systems of detection in this garage were absolutely useless to look into this. They could not pick up heat, they could not pick up particles, they could not pick up presence of charged particles, they could not do anything. By the time they saw it, I don't know if you saw it, they had about 3 seconds to respond. So we don't have 3 seconds response systems. And if you get an alarm and you have 3 seconds to do something, it's almost equivalent as not getting the alarm. So this type of batteries makes detection, it renders detection useless. When you have a fire this fast, the detection that we have right now, which we like so much and we depend on, it's almost like you didn't have it. Now, you have it might make you, oh, I have detection, good. It's like, well, just letting you know that, but this type of fires, by the time you detect, the trouble has already happened and the fire is size that you might feel uncomfortable. But that's not enough. It's not just the initiation route is unusual and very fast. It's that the gases that are being released are very toxic. No human has ever seen a smoke that is not toxic. So all smokes are toxic. Even the one that we have a clean stove, still the smoke is toxic. It's all degrees of toxicity. Batteries produce some of the most toxic gases. Sometimes the battery wall doesn't call it smoke that we have ever seen. And it's a very concerning level of toxicity. When chemists look into this, their eyes, for a chemist, they actually roll. They say, you had what, you said, in the mixture? So it's a very concerning lethal system. The rate of spread, because they can produce jet fires. So it's not only that it spreads nicely as we do, oh, look, it's a two-dimensional spread, look, oh, it's a little bit. Well, they actually produce jet flames. A jet flame is that all the fire goes in one specific direction. You can actually make the flames maybe 3 meters long. Oh, it's only, they typically, don't worry, the fire is only half a megawatt. It's like, yeah, but it's half a megawatt in 10 centimeters, not 3 meters long jet fire. I'm concerned about this. Jet fires means that you can have a rate of spread and going from one car to the other, from one package to the other, from one rack to the other, at a very, really fast spread. That actually uniformly spreading flame spread with our T square laws would actually not be captured. The duration is very unusual. The duration, and I think you're familiar with this, you have some state-of-the-art research on the topic. These fires can last for a very long time. We actually had to create the concept of stranded energy, which is the system still has electrochemical energy stored. It has not been converted into heat. You cannot say that the fire has finished because you still have the stranded energy. You have to wait for all that energy to come out, right? So these fires could last with cars, for example, could last for days. If one of these very large batteries that are trying to stabilize the grid get on fire, we're talking about actually several weeks, if not months, the concept of stranded energy. And then the last one, suppression. That there is this old controversy that the systems of suppression that we have, that we know and we are so proud, that work for oil and gas and marine and buildings and aeronautics, they suddenly are not working well or as well as we wish them to when there is a battery. And there is a race, literally now, there is a race to explain what is happening. People come out with explanations, but the current state of the art is that we don't know how to suppress these fires. It's an innovation. It's a hazard, it's not an innovative hazard. It's a new hazard, and we need to learn. We're catching up to see how to suppress it. So these fires, some people say, oh, they're not particularly scary. They're not very large. Well, because it cannot be detected. It cannot be compartmentalized. It cannot be suppressed. They last very long, and they're very toxic. I'm very concerned about battery fires. No matter that the number is very small, oh, it's 1 out of a million. And I know Elena will agree on this, is the risk, right, is frequency times consequences. So you will see industry who don't want to be engaged on this, and they prefer this to remain blind to us. They always say the frequency is low. And that's true. And it's uncontroversial that the frequency of these fires is low. But what about the consequences? What about the other part of the risk? What if you have a whole garage being lost, as is happening in some places because one of these rare events is happening? Then the risk might actually be of the same level of risk of fuel vehicles, or, for example, the drama that electric vehicles are replacing fuel vehicles, and that's a good change. But they're not replacing anything in other technologies. They're enabling new technologies. The battery that we have here, the batteries that we have in our phone, these are new technologies, they're add-ons, right? They're not displacing anything. They're just adding to the risk. So when we look into the problem, we can see electric vehicles, and I know DBI is very interested in this. All brands have been having issues. They suffer the consequences that it is unusual to see an electric car on fire, and they're very pretty, and they're very flashy, and it means that photos go in social media and spread way faster than if it's a diesel car burning. Diesel car is burning, no one cares, whatever. But if it's a Tesla, if it's one of these other cars, then everybody wants to tell everybody that they saw one of these cars on fire. So this news, these images travel the world, probably giving us the impression that in reality, there are not that many fires. It's just that when they happen, we spread them very quickly. But it's not all just the vehicles. This is what happened. You probably remember what happened to Boeing when literally the week that they released the new airplane, the 787, amazing, I remember vividly, all around the world. They were going to start flying at the same time. They've been training for this for years. They were all ready to go. It was an incredible preparation. And the same week that they start to fly, it's the same week that the batteries, which was one of the innovations of the 787, started to catch fire. And 3 days later, the whole fleet, the worldwide fleet of a new airplane had to be put back into airports for several months until they figured out what the hell was happening. And in a rush, there was a rush of research, and I literally mean research and testing and computer models and absolute desperation to contain the system without modifying the design of the aircraft. I have to say, no one knows very well what they did, but it's true that after 3 months they fixed it, and they went to almost zero fires in in the battery. So for us scientists, we could learn so much by what they did, right? Because they found something after having a mistake. But they don't go to conferences telling us how they almost bankrupt Boeing and then they rescue it. That's not, they don't consider to be a beautiful story. And it's not just Boeing or electric vehicles. It's literally every single use of electric batteries has suffered one of these. These are actually the cases that make it to the news. So you can actually go, not in the literature, scientific literature, but in the news. You go to the BBC, The Guardian, the New York Times, and you see them. They're so big, they're actually in the news. I want to highlight a few of you. For example, Nokia. I don't know if you remember, Nokia almost goes bankrupt because, no, it was, sorry, Samsung, sorry. Samsung over here. Samsung, you probably remember this, right? Some of you might actually be the owners of a Samsung. It almost go bankrupt because they released a new fancy model that suddenly started to catch fire. And I remember vividly being in a flight in the United States. We were about to take off, and the captain announced that if there was in the room, in the airplane, someone that owns a Samsung Galaxy something, 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 this person had to immediately surrender their phone to the staff, otherwise the airplane was not taking off. And I was so happy that I didn't have a Samsung because I just didn't want anyone to look at me kind of like, is that a Galaxy 77? So very scary. Obviously there was a recall. This Samsung, you cannot find it anymore. It's probably been destroyed somewhere in a bunker. But Samsung recovered. They said that it was a defect. It's not our fault. It was a defect. It's like, yeah, sure. As an engineer, I know what you mean. So it was, they screw it up and they fix it. It's called, yeah. Another case that you might want to call the attention is the scooters or the hoverboards. Now it's the scooters, but actually once upon a time there was hoverboards. I don't know if you remember. They were very inexpensive batteries. People actually realized that they love these hoverboards because they can actually, the kids, it was a typical Christmas and gift. They could actually go into the hoverboards until they started to catch fire. And then they didn't forbid the batteries. They didn't say forbidden batteries that are low quality, that are coming from countries without a standard. They say forbidden to have electric hoverboards, right? Which was so specific, I feel uncomfortable. It's like the problem is not the hoverboard, obviously. The problem is the battery. So now we have the same. They say, oh, no, it's scooters. It's like, well, the problem is not the scooter. The problem is the battery in the scooter, no? Some people might have a scooter with a great battery. No, some people we know have a scooter with a crappy battery or they're not taking care of the battery. No, and we should not be just generalized. It's not the system, it's the component that is causing a problem. Other case I want to highlight that you might not be familiar, it was big for us in our research at Hayes Lab, is that batteries also catch fire when they just were born. So batteries are produced by the thousands from battery manufacturing sites, and they have to be stored for different reasons. And they're stored in very large volumes for maybe weeks, if they're unlucky for months. And they started to catch fire. And this is very dramatic because first it's very difficult to hide this from happening because these are very large storage facilities and they produce very large plume. And the second one is that the losses are very large. People don't die from these fires, we're very lucky about this, but the losses, the property loss, the numbers goes into the millions very quickly, starting to touch into the billions because of how much is lost in each of these fires. And the question is, but these batteries were not mistreated. They had not been used yet. They were brand new, highest quality. They were not charged or discharged. They were actually stored. And they were packed, they were protected, and there were no users doing nasty things to them. Why were these batteries catching fire? Right? And it's not just one or two. They were actually happening all around the world, and they continue happening. We stopped doing this in 2019, I think, but they continue happening. And they have fires when they are born. They have fires when they are being used. They even have fires when they are dead. When we throw the batteries, we should not be doing this, but it's taking us a while for society to realize this. Lithium-ion batteries do not go into the garbage. Why? Because we think they're dead, we think we don't want them, we want them to go away from us, but they remain being reactive, they remain having energy inside, no matter how little we think it is, and because now they are being part of the waste, they are mistreated. They are being turned around, they're being hit, they're being squashed, they're being broken, and they are catching fire. And we have an unprecedented number of fires in waste facilities. This in the UK is very bad, by the way. And when they look into the site where the fire started, after fighting the fire for a month, stinking the whole community because it's waste that is burning, they typically find that actually there are batteries that started this, to the point that we have this commercial, it's a commercial from the UK, they call them zombie fires. They say, stop zombie batteries in their trucks, which means don't put them in the waste, because if you go into the waste, they're going to be mistreated and they're going to cause a fire at some point. So it is a topic that even when they are dead, they continue causing fires. So this is a blind spot, right? Most people didn't know about this. In the year 2016, I was asked by NFPA. They said, well, Guillermo, you're an academic, you have a Spanish accent. No, that's not related. You are the editor of Fire Technology, which is the journal of NFPA. They said, why don't you go around your network and ask them what are the things that the fire engineers are worried about. So I went through my network and I said, tell me the things that you are most worried about. No, like, there was a very long list of about 50 things. And I said, from the 50 things, order them, the ones that you worry the most, the ones that you worry the least. And it was a fascinating survey, I have to say. So everybody had a lot of opinions. But look into the ones that they worry the most. This was in the year 2016. They worry the most about new architecture, because architects are always making our lives, fire engineers, more difficult. Timber buildings in the year 2016 was already number 2. In the survey, I was like, what happens with timber? Right? Another blind spot. Building facades was number 3. This was the year before Grenfell. Okay, I was thinking, but what's the problem with building facades? Boom. Right? I learned the year after. Battery fires, battery energy storage was the number 4. So this is a blind spot to the people who didn't want to look into this. Fire engineers already knew that something was happening with batteries, already in the year 2016. Okay? So this was ahead of time. Why do they ignite? I mean, some of you are truly experts on the topic, but I just want to give you an idea. We see thermal runaway as ignition. It's not just an opinion. Professor Semenov got a Nobel Prize in 1956 for proving mathematically that ignition is a thermal event followed from thermal runaway. So thermal runaway is ignition, and I say this is a big thing for me, because if you read a paper from Battery Wall, they don't say the word ignition. They don't say the word fire. They don't say the word flame. They don't say the word smoke. It's like this pristine paper that is talking about battery fires without using any keyword that you could find. They're called thermal runaway, thermal events, gases release, and they use all these names to avoid saying what it is, right? And I don't think they do it on purpose. They're not themselves, these scientists are great scientists, by the way, I know them. They're not doing this on purpose, kind of like, how do I avoid it? I think it's psychological. They say, if I say fire, my people stop inviting me to talks. If I say thermal runaway, they allow me into the room. So they themselves realize, this is how I can continue being in this room, by saying thermal runaway. If I say fire, we are not invited as often, because we say fire, that's the fire guy, right? But in this room, we are fine, because obviously you do fire. And the problem is when a battery is always releasing some amount of heat, right? This is unintended consequence, a little bit, and it's fine. Batteries, well designed, can handle a little bit of heat because of side reactions or ohmic losses. The problem is when this amount of heat starts to go, uncontrolled, and when the amount of heat that is being released is higher than the rate of cooling, because then the temperature increases. And you might have a reaction that is exponential, a Arrhenius reaction rate, for example, and then you have a thermal runaway. The more heats up, the more it releases, and the less you can cool. And actually that accelerated in time, maybe in an hour, or maybe in 3 days, or maybe in a week, ends up in a fire that you can see even with the flames outside. So it's an imbalance of heat. You have different reasons why the battery releases heat. No, it's not just one. And this has led in the battery community to identify 3 main scenarios at which ignition can happen. They don't call them ignition, they don't call it hazard, they don't call it accident. They call them abuse conditions. What do they call it abuse? Because it is unintended. So if it's unintended, someone did it. This is how they think about this, right? So when they say abuse, they're actually thinking of us, of the users. They said, I designed a beautiful thing. When you guys, users, are not here, this battery doesn't do anything bad. If it does, it's because you users abuse it. Abuse it electrically. Why do you charge so fast? Why do you discharge so? You have to be gentle in the way you use it electrically. Or mechanically. Are you mistreating the battery and giving it heat and putting a nail through it? Because then, obviously, we'll get upset and we'll show its reactivity. Or thermal abuse. Don't put the batteries in the oven, right? Batteries are not meant to be in the oven. I'm exaggerating it, but really this is what they're telling us. All these cases are reactions that were unintended that suddenly go through the thermal way instead of the electrical way. Then they can also have defects. which is how industry defends themselves. Oh, sorry, I didn't mean that. There's an effect in one battery out of 1,000, but the other ones are fine. And in reality, what happens, this is how I understand battery fires. It's a specific bias that I have, is I see all of these cases as cases of self-heating ignition. This was the Nobel Prize of Semenov and then followed by Frank Kamenetsky, which is that the system itself can heat up and release energy until it runs to thermal escape, which is the concept of thermal runaway. And at some point in a few years, I was going to say decades, people will be able to unify all these scenarios into self-heating, which is how we quantify, for example, when we want to quantify the chemical reactions that are happening in those scenarios, we actually go to the fundamental level and we couple the chemistry with the heat transfer. So this is how we see it. And for example, the work of my group has focused on here. When we go into the literature, they talk about this, and always reviewer says, but which abuse condition is this? It's not an abuse condition, it's the fundamental reactivity of the material. We do it with polymers, we do it with all these reactive materials, right? And this is important, because I'm gonna tell you a story. So this is an experiment that we conducted in the group. Francesco was a co-author of this work. And what we did is we put this temperature, critical temperature, and we took one battery, one cell, we bought them commercially, we didn't do it ourselves. First, because we don't know how to do it. And second is because if you do fire research with your own batteries, it's going to be always your fault. So we went to Amazon. We bought a decent battery. Now we realize that it was too decent because it's actually so very safe. We called one cell. We put it into the oven, and we started to heat up the oven. This is Frank Kamenetsky analysis. Until we increase the temperature of the oven until the battery, very slowly, Francesco is an expert at doing this, until the battery ignites. The thermal runaway, that's what they mean, right? And it reached a temperature of 165 Celsius. So two things about this. When we went to the literature and we say, dear experiment batteries, your battery will self-ignite, self-heat to ignition. If you store it at a temperature of 165 Celsius, you will have a fire. And they say, that's fine. We never store our batteries at 165. You are not meant to have the battery at 165. So that's true. You know this foam over here? You think it's flammable? Yeah, it's flammable. You know it ignites? It ignites at 300 Celsius. So you are not concerned about that foam. Sorry, you are concerned about that foam that ignites at 300 Celsius. You're not concerned about one cell that ignites at half the temperature in Celsius. And they're like, oh, wow. So this is more reactive than the materials that we know are reactive to begin with. But the second one is that what happens if you put two batteries? They say nothing, because two batteries, they will ignite at 165. So we did the experiment, and they start to ignite at 160. And if we put 3 batteries, 4 batteries, why is the critical temperature decreases? Why the batteries are stuck together? They're not connected. They're not charging or discharging. They're just literally being friends to each other. They're just 1 and 2, like literally by the hand, well, a little bit more compact, right? Why is it that more batteries lower the critical temperature? And this for battery people is magic. They say first, they say, Guillermo, do the experiments again because I think you did it wrong, right? All of them, they literally say, the standard, they say, Guillermo, the standard says that all of them should have 165. So everything here, Guillermo, just go back because you don't know how to do experiments. And actually, what happens is Frank Kamenetsky. Frank Kamenetsky says that it is the heat transfer, the inability of the system to cool as you make it big that makes the critical temperature lower. And this is for 4. How many batteries you think are in a rack in a massive storage facility? You think they have 4 million batteries together. So this is what we did. We were not allowed to burn 1 million batteries together, I wish, right? And we don't have the money, nor the facilities, nor anything, not even the will. So what we do is we took Frank Kamenetsky theory, which we love it, right? It's fundamental fire science. We're not inventing it. We took our little experiments over here, and we extrapolate using Frank Kamenetsky. And then what you start to get is, you start to get into a realm where the batteries could self-ignite at room temperature in a place like Spain, for example, where the average temperature might be in the summer for 40 Celsius. And then we went to the battery wall. It's a fascinating conversation. They didn't like the 165. They didn't like that the temperature drops with the size. They didn't like any of this. When they look into this, they were just literally laughing in the room. They was like, but Guillermo, who puts 100 meters of batteries all together? Well, I could show you the photos of the storage. I said, this was a commercial battery, brand new, of a really reliable manufacturer with really high standards. And I think the 4 batteries plus the repeats, the 20 batteries that we use had no defects. What if I ran this curve and these experiments with a battery that is aged, mistreated, defective, or low quality manufacturer? Then this curve starts to be like this, and this curve starts to be like this. And then we cross the ambient temperature for self-heating at maybe the size of a box of batteries. And that is what I'm concerned about. I'm not concerned about the batteries that we chose, which unfortunately, as I told you, they were too good for what we wanted to do. But I'm concerned about the ones that maybe this manufacturer will not be selling us because it will be illegal maybe or extremely dangerous to sell. And then not only you can have ignition, but you can have, these are experiments from Stellarov in Maryland. You can have that if you have batteries all together, one of them, the weakest, the one in the middle because it loses less heat, the one that is oldest, the one that is weirder, but one of them ignites and then the fire starts to spread from one battery to the other. They say this propagation of thermal runaway. We also call it fire spread, right? So they change the names. Everything is changed in battery wall. They mean exactly the same. And then you can have concatenation, and the idea is, well, you have failure stopping one of the batteries as a prevention breach, but you might want to stop the propagation. That in fire engineering is called compartmentation. So you make sure that the separation between the batteries, thermally or otherwise, is such that one of them fails, one pack or unit fails, but not the whole battery pack fails. And this is the concept that I want to tell you, because people say, well, Guillermo, you've told us, this is very often, you're bringing enough bad news. Yeah? Can you please stop telling us all the bad news? Can you tell us the good news? And the good news is just let fire engineers do what they know how to do, using the following, for example, of layers of protection, where you have the hazard here, the fire, and you have the people and their property here, and you put in the middle as many things as you can. And the many things that you can put can be, conceptually speaking, divided into 6. It could be that it's prevention, batteries that are not reactive, for example, or batteries that are not allowed to be abused because they are more, they are stronger. Or you can actually have detection, which for batteries is a hazard. Conventional detection is too slow, so you have to put the detection in the battery. And it happens that most batteries have thermal management, have even little computers and microchips and sensors inside. Use those sensors to detect as soon as possible. If there is a detection, you might have to evacuate from the room where it is happening very fast. You might want to compartmentalize from the package, the battery, but also if the battery happens to be in a room or happens to be in an airplane that is flying, you might want to compartmentalize. You might want to apply suppression. And if all these have failed, you at least have a structural resistance or the ability to absorb damage. This, for example, if you're in a ship, you don't want it to sink. If you're in an airplane, you want it to be able to land. If you're in a car, you want it to, to make sure that it's out of the road and out of trouble. And this is how the layers of protection will look in a battery. And this is another topic, and these two things combine together. These are the sizes, right? You can go from the material to the components, the electrodes, to you put them together, and finally you have a cell. Then you put cells together, and you have the jolly roll. You can actually put them together into module, and you have the pack. And we'll have all these sizes. So we humans are mostly in this realm. This is where the true hazard is. 95% of the research of fire safety is in this realm. And this is a problem, because in this realm, you can do only material science, you can only do prevention. In this realm, you cannot do detection, you cannot do suppression, you cannot do compartmentation, you cannot do absorption of damage. You can only do prevention, which means that we know something about prevention at the smallest scale, and we know very little to nothing about detection, compartmentation, suppression, and damage control at the scale that we care about. And this creates an imbalance between the hazard and what the industry is interested about. So we formally did this in a meta-review, and a meta-review is a review of reviews. The topic is advancing so fast that we just don't do reviews. We actually take all the reviews that someone else has done, we put them together, and you review them. So what we did is these graphs over here, each of these columns is a review. So it's two tables. Each of them is a review. And what we show here is, for example, where is the, okay. So P is prevention, D detection, S suppression, C compartmentation. So this is, in this review, you can see most of the research was on prevention, a little bit on detection, nothing on suppression, nothing on compartmentation. And you can look into all of them, and you can see that all of them have a peak in prevention and they have very little afterwards. You look into sizes here, the causes of ignition are mechanical, electrical, thermal, on short circuit. You can look into all of them and you can see that they vary in range, but the one that is the most popular is the electrical abuse. They love to study the electrical abuse, but what are the other ones that are actually less studied? And when you look into the size, you also see that they like to look into the smaller scale. So that is one of the issues that we have found. Although there is some research in battery fires, the research has a massive bias towards small and prevention, and it doesn't address what we fire engineers truly want to do, which is to stop the fire when it has already breached prevention. And for a long time, for a very long time actually, I've been facing denial from industry. Not for fire engineers, but from industry. The guys who are manufacturing the device and are selling it for us for a good price, there is a significant amount of denial. Denial at least from the factory outwards. I know when they hire our students that from the factory inwards, they are really concerned about fire because they hire our students. Our students cannot tell us what they do, but they tell us, Guillermo, this is Apple, General Motors, Tesla. They tell us we are very active doing fire safety inside headquarters. We are not allowed to tell you absolutely anything about this. And when they go to give their big talks, they never say, we are releasing a new model, which is safer than the previous one, because instead of killing 100 people, no, you cannot say this publicly, right? Because you are, first, the PR damage is incredible. You will be kicked out of the conference. But also, you cannot say that you've been selling one that was dangerous and pay more for this one because it's safer. It's unsellable, right? There is no market for this. That's why they cannot tell you about it. But for a long time, I was like thinking, what is cost? It's not even, I say, it's not even expensive to address the safety. It's literally not expensive. It's not I'm asking them to create a new type of battery. It's like you can do many things at a simple case. For example, the electrolyte. No, some of the electrolytes are combustible. Some of the electrolytes are combustible, right? You don't have to choose them combustible. Some of them, in this reactive material, they put a liquid itself that actually is combustible. It's like, well, really? Who was thinking about this? You can actually just change the electrolyte. You don't remove the hazard, but you decrease the hazard immediately, right? So then I saw this graph and explained to me a lot. This is the cost in the manufacturing of batteries. And when you see the cost, most of the cost, 50% of the cost is the cathode. This is what the literature is obsessed I'm an electrical engineer. Why are they obsessed about the cathode? Because this is how you can outperform your competitors in price. If you come out with a cathode technology, you can halve the price of the unit. You can multiply by 2 the profit, right? This is why they care about the cathode. The cathode in fire safety, it is important, but it's actually not the most important one. And actually, if it's so expensive to move, well, you don't have to move it. But look what's at the bottom. The housing, which is about all heat transfer. Self-heating is about the housing, how you prevent it from cooling. We look what is the electrolyte. For about 20 years, we had flammable electrolytes, combustible electrolytes. Now we don't. Why? Because there was no market for 4%. They don't care. It's like, we don't talk about fire safety. No one is a blind spot. No one is telling us about fire safety. And I don't gain anything from my market by changing it, right? And the other one is separator. The separator actually sometimes is a polymer, so it contributes to this. And the anode, which has almost the same role as the cathode. So they were not caring about safety because there was no benefit for them. We, as a professionals, society, authorities, were not asking them to do safety, and there was no benefit for them, so they were not doing it. So I've talked to you about blind spots. I do think that batteries are a blind spot. I think that we cannot see them in many places statistically, but in Vancouver, in London, in New York, now they are appearing even in the databases. It means that actually it's the elephant in the room by the time you can see them. That research is focusing on prevention of a small scale, and we are literally left to our own devices at the large scale, suppression, compartmentation, and detection. And that I know in this room everybody agrees with me, that as a scientist, if we understand the hazard, we understand the enemy, the fire, right? We replicate it in safe conditions and we observe them in detail in the computer and in the experiments, then we can actually lead to safety, which for me is uncontroversial. It leads to a better product. But this is for society to decide, right? And the last thing is that if industry cannot solve this problem, they will be forced to solve it, and standards and intervention into the market will start to appear. This freaks them out. This is like the word that you cannot mention, more standards and intervention into the market. But I know that they were invented, standards and intervention in the market were invented that if industry cannot solve it themselves, and they keep bringing this hazard and deny it, we will force them to solve it by bringing more standards and more red tape, as they call it. And with this, I finish. Thank you very much. And if you have questions,